All right, here we go. This is the end of the course, or at least the beginning of the end. This last section is all about taking Taylor series that we know and working them together in different ways to create Taylor series of other functions without having to, take a gazillion derivatives each time, right? In order to do a Taylor series, you need to know the derivatives, all the derivatives at the point you're centering around. But we're going to try to get past that and find a few easier ways to do a few things. Okay. Now there'll be time for some functions that you have no option except to take derivatives and plug in b, right? But here we go. Let's take a look at the Taylor series that we've run across a couple times already here. E to the x is 1 plus x squared over 2 plus x cubed over 3 factorial x plus x to the fourth over 4 factorial plus, and so on. The nth term would be x to the n over n factorial, right? Just keep going forever. I want to look at the function e to the minus x. But I can think of e to the minus x as just e to the x with x being replaced by minus x. This video is about composition, right? We're going to be putting one function inside of another. And so if I just replace all the x's here in this equation with minus x's, the thing is this is true for any value of x I plug in, whether I plug in 2 or minus 2, whether I plug in 7 or minus 7, right? That plug in an x, the left-hand side is equal to the right-hand side. And for this function, the interval of convergence was the whole real line. So that's true. Every value of x, left-hand side equals the right. So I don't care if you call it x or call it minus x. It's still all of the x's, right? But by replacing x by minus x, here, what you see is every time it's x minus x to an odd power, you end up with minus x. But if you have minus x to an even power, it just becomes positive x. So positive x squared or positive x to the fourth, right? So here we go. So e to the minus x, the Maclaurin series, or the Taylor series centered at 0, is 1 minus x plus x squared over 2 minus x cubed over 3 factorial plus x to the fourth over 4 factorial minus, and so on, right? Just plus or minus of what you had up here, alternating signs on the terms. Likewise, we could take a look at 1 over 1 minus x. This was the ice cream theorem, right? This is 1 plus x squared plus x cubed plus x to the fourth. Again, Maclaurin series or Taylor series centered at 0. And again, I want to replace all the x's by minus x's. Now this is not quite the same as the last one because the interval of convergence on the last one was the whole real line. Where here we just have the interval of convergence is from minus 1 to 1, not including the endpoints. But at least within that range, replacing x by minus x, again, minus 1 to 1 is symmetric about the origin. So any point in that interval, you can take the minus and you're still going to be in that interval. So I feel okay doing this. So if I look at 1 over 1 plus x, that's actually 1 over 1 minus minus x. So there is now this x being replaced by minus x. And so I'm going to replace all of these x's by minus x's. And there we go, all the way across. And again, minus x to an even power is going to be positive x to that power, and minus x to an odd power is going to be minus x to that power. And so what we end up with is an alternating sum, 1 minus x plus x squared minus x cubed plus x to the fourth, and so on. Right? And we're going to go a little bit further, extend that one a little further. And so now that I've got this 1 plus x squared, what if I replace all my x's by x squareds? And notice, again, I'm looking at the interval from minus 1 to 1, and if you take a number between minus 1 and square it, you're still between minus 1 and 1. So it makes sense here for me to do this as long as x is within the interval of convergence of this Taylor series or Maclaurin series. So from this function, from this equation right here, I'm replacing all my x's, both left side and right side, with x squareds. And I get 1 over 1 plus x squared is 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth. Now I have only even powers being added up in an alternating sort of way, plus minus plus minus. The reason I like this 1 over 1 plus x squared, well, I mean, several reasons. It's kind of a cool graph. It's a bump function. But it's also the derivative of the arctangent, which I'm going to get to in a future video. But anyway, I got to here not by taking the derivative of this thing, and then taking the derivative and taking the derivative and each time plugging 0 in to see what the derivative was. I mean, I could do that. It gets a bit more and more complicated each time. The first derivative is not too hard to do. But the chain rule is going to keep popping out at times 2x. That ends up in the numerator, and then, yeah, then you're going to have quotient rules, and it's going to get more and more complicated each time. So anyway, this was pretty straightforward getting here. Just started with 1 over 1 minus x, to turn it into 1 over 1 plus x, to turn it into 1 over 1 plus x squared by just replacing x by something else which would be of use to me. Okay. I'm going to continue on this vein and say I can do 1 over 1 plus anything linear, 1 over anything linear, let me say, as follows. So I'm going to have 1 over a plus bx. A and b are just constants and I'm not telling you what they are. Factor an a out of the bottom, looks like this. I can rewrite this as 1 over a times this fraction here. And then what I'm seeing is this 1 over 1 plus bx over a is this one that's right at the top of the page, but instead of an x here, I've got a bx over a, or a over b times x, however you want to do that. So I'm replacing this right-hand side. All the x's are being replaced by b over a times x, b over a times x, b over a times x. Then doing some algebra here, right? You're going to have a b squared x squared over a squared, a b cubed x cubed over a cubed, and so on down the line here. The whole thing's going to be times 1 over a, so I distribute that in, and I've got a Maclaurin series, or Taylor series centered at 0, for this 1 over a plus bx. We should point out that the interval of convergence here is not the same as it was to begin with. Now, the first two we did, definitely the interval of convergence was still the same. Replacing x by minus x just swaps the x's, positive x's for negatives and vice versa. So the convergence is still that same interval. And remember, we got that interval of convergence by noting that geometric series converge when that constant multiplier is less than 1, right? So that you go from one term to the next, you're always multiplying by the same thing. In this one, you're always multiplying by x. In this one right here, you're always multiplying by minus x. In this one right here, you're always multiplying from one term to the next. You're multiplying by negative bx over a. The power of b increases one time, the power of x increases 1, and the power of a increases 1 each time. And then it changes from plus or minus 1, so you're multiplying by minus in there as well. So what I need is I need that bx over a to be somewhere between minus 1 and plus 1, which puts x now between negative a over b to plus a over b. So depending on what the values of b are, you've taken that interval from minus 1 to 1 and either stretched it or squeezed it accordingly. Okay, so that's what I want to say about composition. That is, we can take these functions. You know, we could do, for instance, take sine x. We know sine x, we know cosine x. We could do sine of 2x or the sine of x squared just by replacing the x by 2x or x squared in that Taylor series that we know. Maclaurin series, I guess, is what we really do. Right? So there we go. There's an introduction to composition.